Hey everyone! Welcome back to Deep Dive. In part 1, we dove headfirst into the world of embedded hardware interview questions, covering the basics. But you guys know we don't do just basic here on Deep Dive. So buckle up, because in this part 2, we're cranking things up a notch. We're talking advanced topics, practical scenarios, and the kind of questions that can really make you stand out from the crowd. If you missed part 1, don't even worry about it. There should be a card popping up on screen right now. Click that and you'll be all caught up. You're welcome. Alright, first up, let's talk about the heart of any embedded system, the brains of the operation. We're talking about microcontrollers and microprocessors. Now, you might think they're basically the same thing, right? Wrong. They both have micro in the name, and they both handle processing, but they have some key differences. A microcontroller, or MCU, is like a Swiss Army knife. It's got everything built in, your processor, memory, and all sorts of peripherals, all in one tiny package. Think of it like your smartphone. It's self-contained, power-efficient, and perfect for embedded applications where space is tight and you don't need a ton of processing power. On the other hand, a microprocessor is more like a powerful desktop computer CPU. It's all about raw processing power, but it needs external components like RAM and storage to really shine. You'd use a microprocessor when you need serious horsepower for things like image processing, complex algorithms, or running a full-blown operating system. Next up, we're going to dive into the world of memory mapping. Now, this might sound a bit dry, but trust me, it's super important. Basically, memory mapping is how your embedded system knows where everything is. It's like a virtual map that connects your processor to all the different peripherals and memory locations. There are two main ways to do this: memory-mapped I/O and port-mapped I/O. With memory-mapped I/O, everything, and I mean everything, is treated as a memory location. You want to talk to your sensor? Just write to its memory address. Need to grab some data from memory? Same deal, just read from the right address. It's simple, elegant, and keeps your code nice and clean. Port-mapped I/O, on the other hand, is a bit more old school. You have dedicated ports that are hardwired to specific peripherals. It's a bit more complex to manage, but it can be more efficient for certain applications. Let's be real, nobody likes interruptions. But in the world of embedded systems, interrupts are crucial. They're like the little alarms that tell your processor to stop what it's doing and pay attention to something important. Think of it like this. You're working on a complex spreadsheet, totally in the zone, when suddenly your smoke alarm goes off. You're not going to ignore that, right? You're going to drop everything and deal with the potential fire hazard. That's what an interrupt does for your embedded system. It tells your processor, hey, hold up, something needs your attention right now. Now, there are different types of interrupts. You've got your maskable interrupts, which are like those annoying telemarketers you can just ignore. And then you've got your non-maskable interrupts, which are more like those urgent phone calls you absolutely cannot miss. When it comes to interrupts, latency is key. That's the time it takes for your system to respond to an interrupt. The lower the latency, the faster your system can react, which is crucial for real-time applications. Okay, let's talk about power optimization. This is super important, especially for battery-powered devices. You want your device to last as long as possible on a single charge, right? Of course you do. So how do we squeeze every last drop of juice out of our embedded system? Well, there are a bunch of techniques we can use. One common approach is to choose the right clock speed. Think of it like your car's engine. The faster you go, the more fuel you burn. Same with your processor. The higher the clock speed, the more power it consumes. So if you don't need the full speed, slow things down. Another trick is to use sleep modes. When your system is idle, why waste power? Put it to sleep. You've got different sleep modes too, like light sleep where it can wake up quickly, or deep sleep where it sips power like a camel in the desert. Now let's talk about oscillators and clocks. These are the little guys that keep your entire system in sync. You see, every digital circuit needs a clock signal to function. It's like the conductor of an orchestra making sure everyone's playing in time. There are different types of oscillators, but the two most common ones are crystal oscillators and RC oscillators. Crystal oscillators are like the fancy, expensive watches of the oscillator world. They're super accurate and stable. which is crucial for applications where timing is critical, like communication protocols. RC oscillators, on the other hand, are more like your trusty everyday quartz watch. They're cheaper and simpler, but they're not as accurate. So, how do you choose the right oscillator for your design? Well, it all comes down to your specific requirements. Need extreme accuracy? Go crystal. On a tight budget? RC might be the way to go. Alright, let's move on to bus systems. These are the highways of your embedded system, carrying data between different components. You've got your parallel buses, which are like multi-lane highways, and your serial buses, which are more like those scenic two-lane roads. Three of the most common serial buses are SPI, I2C, and UART. SPI, or Serial Peripheral Interface, is like the express lane. It's super fast and efficient, perfect for high-speed data transfers. I2C, or Inter-Integrated Circuit, is more like a shared bus route. It's slower than SPI, but it can handle multiple devices on the same bus, which is great for things like sensors and displays. UART, or Universal Asynchronous Receiver Transmitter, is like the long-haul trucker of the bus world. It's designed for sending data over long distances, like between your computer and a GPS module. Next up, we're talking about signal integrity. This is all about making sure your signals arrive at their destination clean and clear, without any distortion or interference. Think of it like this. You're trying to have a conversation in a noisy room. If the noise is too loud, it's going to be tough to hear what the other person is saying. Same with your signals. If there's too much noise or interference, your data can get corrupted. So, how do we maintain signal integrity? Well, it all starts with good PCB design. You want to keep your signal traces short and direct, avoid sharp corners, and use proper grounding techniques. You also want to be mindful of things like crosstalk, which is when signals on adjacent traces interfere with each other. Now, let's talk about ADCs and DACs. These are the bridges between the analog and digital worlds. An ADC, or analog to digital converter, takes a continuous analog signal like the voltage from a sensor and converts it into a digital representation that your microcontroller can understand. A DAC, or digital to analog converter, does the opposite. It takes a digital signal and converts it into an analog voltage or current. ADCs come in all shapes and sizes, with different resolutions, sampling rates, and accuracy levels. You've got your SR ADCs, which are like the workhorses of the ADC world, and your Delta Sigma ADCs, which are known for their high resolution and accuracy. Let's face it, debugging is part of life when you're an embedded systems engineer. No matter how good you are, you're going to run into bugs. It's just a fact of life. But fear not, there are tools and techniques that can help us track down those pesky bugs and squash them like, well, you get the idea. One of the most essential tools in our debugging arsenal is a JTAG debugger. This little guy lets us connect to our embedded system and see what's going on inside. We can step through our code line by line, inspect variables, and even modify memory contents on the fly. It's like having X-ray vision into the inner workings of our system. Finally, let's talk about PCB design. This is where it all comes together. A well-designed PCB is essential for any embedded system. It's not just about connecting the dots, it's about creating a robust and reliable foundation for your entire system. One of the most important aspects of PCB design is power distribution. You want to make sure that all of your components are getting the power they need without introducing noise or voltage drops. This means using wide traces for your power rails, placing decoupling capacitors strategically, and paying attention to the overall layout. Another crucial aspect is signal routing. You want to keep your signal traces as short and direct as possible, while avoiding sharp corners and vias, which can introduce reflections and signal degradation. And of course, grounding is super important. A good ground plane helps to reduce noise and crosstalk, ensuring that your signals stay clean and clear. Well, there you have it, folks. Another 10 embedded hardware interview questions to add to your arsenal. I hope you found this video helpful. If you did, be sure to give it a big thumbs up and let me know in the comments what other questions you'd like me to cover in future videos. Don't forget to subscribe to Deep Dive for more awesome embedded systems content. Because guess what? We're not done yet. In part 3, we're going even deeper, covering even more advanced topics that will really make you shine in your next interview. Until then, keep on learning, keep on building, and keep on pushing the boundaries of what's possible with embedded systems.